Well, friends of mathematics, today we're talking about Math 105, section 5.3, and we're going to be looking at the logarithm as a function and really making a list of things that are true to logs. Now, in order to play with logs, to start out, I'm going to draw a parent function. And the parent function that I'm going to draw here is y is equal to 10 to the x. And we know that we have an inverse function, and our inverse function, I guess I can call this f of x, is equal to this. And normally I would write that f inverse of y is equal to the log of y. But what I want to do is I want us to be able to visualize the parent function and the inverse function on the same set of axes. And so I'm going to look at f inverse of x equal the log of x. And as you know, when I take an inverse, I am really reflecting over the line y equals x. And so we have this horizontal asymptote, and when I judo flip that thing, it's going to lead to a vertical asymptote. Let's look at this. Here we have the point 0, 1, and the corresponding point on logarithm is going to be 1, 0, just like we talked about in that identity property. I guess the next point would be 110. I'm completely out of scale here, but we would have the point 110. And on logarithm, the corresponding point would be 10, 1. My scale is terrible here, but exponential goes like so. Log goes like that. The same is true if I was going to look at this for natural log and e to the x. If I have e to the x right here, I certainly have the point 0, 1. 0 goes in, 1 comes out. I have the point 1, comma, e. 1 goes in, e comes out. And so if I'm going to make my inverse function, which is natural log, I'm certainly going to get the point 1, 0. I'm certainly going to get the point e, comma, 1. And now we can say that when I flip this thing over the axis, flipping it, it's going to come correct like this, and we'll have behavior that looks like so. Let's remember for our exponential. Let's say I have 10 to the x as my function. What was the domain here? Well, it turns out I could use all real numbers to go into my exponential function. And the output was from 0, which was not included, to infinity. We got higher and higher and higher. So for our exponential, this was the domain and that was the range. And that's true for e to the x as well. My inverse functions, which are log of x or natural log of x, the domain of these is 0 to infinity. And the range is negative infinity to positive infinity. And I'm going to specify that right here. Domain. 0 to infinity. Range. Negative infinity to positive infinity. And then finally, there's one other thing that we get. Our logs or our exponentials had horizontal asymptotes. And when we do that judo flip, we're going to have a vertical asymptote of y equals, I'm sorry, not y, x equaling 0. X equals 0 is a vertical line right here. And that's really all we have to say about the function log x or natural log x. So we just discussed that logarithms have vertical asymptotes. If this is the natural log of x, we can see that we have this vertical line, x equals 0, that as x gets close to 0, natural log of x, it goes to negative infinity. And that's the definition of a vertical asymptote. As x tends to some value c, if f of x tends to either positive infinity or negative infinity, we have a vertical asymptote. So let's look at something like this. And I'm going to draw a vertical line here. We'll call this x equals 2. And I'm going to have my function do something like this. And on the other hand, do something like that. Now, it's true, as I get close to 2, I go to positive infinity and I go to negative infinity, but we have to specify how we're getting close to 2. And we're going to do that with directional limits. So we can say as x approaches 2 from above. And so the idea here is that we're getting to 2, but we're using values bigger than 2. There are people who also say that this is x approaching 2 from the right. Yeah? So I'm on the right of 2, and I'm getting closer to 2. But the way that we write this notationally in our math class is we write x approaches 2, and there's a superscript plus sign. And that's read as x approaches 2 from the right. So in this case, I can say that we have the limit as x approaches 2 from the right of f of x here. And that's equal to, well, I'm getting closer and closer to 2, but from above 2, and my output is going to negative infinity. And that means that we have a vertical asymptote at x equals 2. Let's go from the other side. Let's go from the other side. And all we're doing now is I'm getting closer and closer to 2, but from below. And we can write that, the limit, as x approaches 2 with a superscript minus. And one way of thinking about that is like I'm using this type of value. I'm getting, first I might be using x equals 1, and then x equals 1.5, and then x is equal to 1.9, and x is equal to 1.99999. And so I'm getting closer and closer and closer to 2, but I'm using values from below 2 or from the left of 2. So what's happening here as I use x values that are closer and closer to 2, but from underneath 2, our function f is blowing up. It's going to infinity.